oil or gas well. So my contact information here is at the top of the slide. If you have questions, feel free to call me or give me an email. Echometer has some online training that's available. We record some of the presentations we've done in the past, and we have a one-day FOLLOWIN class and a one-day introductory dynamometer class. We have about a half-day plunger lift class, and then we have, these are with our new software called TAM, and this is with our old software called TWM. It's a 3-day class that is accessible under support on our webpage. And if you're interested in registering for one of these classes, please contact Kylie at echometer.com. And then also what we've been doing lately is for about the last 12 weeks, we have been doing a thing that we call Ask Echometer. And that's Wednesdays from 2 to 4 p.m. And Carrie Ann has been coordinating that. So if you'd like to register to attend those have their own separate web page, and they're 2 hours long. And we usually select a topic that is of interest to people that are Echometer customers. And then we typically do about a 1-hour presentation followed by an hour of data examples and questions. And you can contact Carrie Ann if you'd like to register to be on the mailing list for that. We had training in Wichita Falls, Texas, and other cities like Odessa and Willis, North Dakota, and many people all over many places all over the United States. And those classes have primarily been canceled for sure so far this year because of the COVID-19. So we're trying to replace these classes with online training. All right. This slide is kind of an interesting slide because we're talking about rod pumping, and we show a profile of a suck rod pumping unit, and we're identifying all the parts. And we're talking about when you go to a well to be successful at analyzing and troubleshooting the well, you can use data to determine what's wrong and solve the problem. And so this presentation is going to talk about how you can become a wizard, and you can look down a small diameter pipe 10,000 foot deep and see what's happening. And so we'll talk about seeing what's happening. Now we use the data we collect at the surface, and the data is collected both with either a wireless system or a wired Echometer system. And the kind of data we collect is there's fluid level with pressures and power, which is volts and current and amps, and then dynamometer data. And we'll talk about all this data a little bit through this presentation. And we want to make sure that we collect the data that's representative of the conditions of the well. So when sometimes you connect equipment to the well, and you may turn the well off for a minute. So you need to get the well turned back on and restabilized so that the data you collect is representative of the normal operation of the well, and not data that just shows that the pump is full because you had it down for a period of time to hook your equipment up. We're going to talk a little bit about the performance of the well and what that means, or the well's potential. And what that means is you can take a fluid level when the well is producing, along with the production rates, and compare that bottom hole pressure to the pressure when the well is shut in, called a static pressure. And we can determine if the well has potential to produce more oil or gas. And also the dynamometer will show you if the pump's not full, if you can produce more oil and gas. And then other things we can use it for to identify ways to reduce operating cost. Now this is a cross-section through your formation and through your well. So here's our wellbore, and here's our formation. And we're showing that the pressure far away from the well is static. It's like this, it doesn't really change. And that's what this is showing. There's the radius of influence at that depth, that distance. So this distance is what we call radius of influence. And then if the well's pumping, then the the pressure, not the liquid level, but the pressure inside this formation is declining, and this is is the declining pressure. We call it drawdown. And then by the pumping equipment lowering the pressure of the wellbore, the fluids flow from the high pressure to the low pressure, and that relationship is called the productivity of the well, the inflow performance of the well. And so in this case, we're showing that the pressure far away is 1,000, and the pressure near at the wellbore is 500 psi, and it's flowing. You can see how the pressure drops fairly slow, and then it drops really quick and near the wellbore. We call it a radial flow inflow performance curve. There's different types of relationships between the drawdown or the producing well pressure compared to the static. And the relationship is that the lower the producing bottom well pressure is compared to the reservoir pressure, the higher the inflow of liquid. And to get more production, you need to increase your drawdown. There's different methods. We use two different methods. One's called the Vogel inflow performance rate relationship, or Vogel IPR. And then there's also one called the PI method, which is a straight line method. And that's the relationship between production and bottom hole pressure. When the well has stabilized performance, that means that the producing well pressure is remaining fairly constant, the flow levels remaining fairly constant, the production rate out of the well is constant. And we can use that stabilized condition to measure the production rate, measure the producing well pressure. If we know the reservoir pressure, then we can calculate the maximum liquid rate from the reservoir. And we use that inflow performance relationship to be able to calculate that as a function of the producing well pressure. And the fluid level could be high or could be low, and the bottom well pressure could be the same, because the bottom well pressure is controlled both by the casing pressure at the surface, the weight of the gas, and the weight of the liquid above the pump. And so, you know, the fluid level can go up or down based on either lowering the casing pressure, it goes up, or the fluid level can go down as you raise the casing pressure if your well's not pumped off. And even if the well's pumped off, sometimes you can lower the casing pressure and get more inflow as you lower the bottom pressure in the well. So here we're talking about, again, stabilized performance, and the bottom pressure here is controlled by your pumping rate, and it's a function, there's a relationship, and the faster you pump, or the bigger pump you have, typically the more liquid you withdraw, and that results in a lower producing well pressure. And the casing pressure, this is a note down here at the bottom, is that the casing pressure doesn't really indicate what the pump intake pressure is, because you need to know how much liquid's above the pump, because the liquid weighs a lot more than the gas. And so that's one of the reasons why you want to shoot a fluid level, is to actually be able to determine what the producing bottom pressure is and what's the pressure at your pump. And you really can't estimate it unless the well is pumped off. All right. And even then, if it's pumped off, the casing pressure is high, it's not really pumped off, because the casing pressure would be pushing on the formation, restricting inflow from the well. All right, so this is the wired system. It's called an Echometer well analyzer. And this is called a remote fire gas gun. We use that to determine distance to liquid or shoot fluid levels. This is a horseshoe load cell. And if you were to step on it, I would weigh you. If I put a 16-ounce Coke bottle on it, it'd weigh a pound. So it's like a bathroom scale. But it's used to weigh the rod string in the well, in the tubing fluid. Now this device is a load cell, but what it does is it measures the diameter change of the polish rod, and that means the load on the rods are changing due to the pump load, and the pumping speed due to acceleration, it changes the load. And so this device doesn't really measure the load, it measures, it's like a micrometer, or very accurate diameter change measurement. And then we use the weight of the rod string and the properties of the rods and the tubing fluids to calculate what the loads are. This is a power probe, and it measures the current and the kW. And these are the 3 voltage connectors and the amp sensors, and that outputs the current that's measured while you're pumping. So here we have the well analyzer on the back of a pickup, and we have the cables going off to these different sensors. And we can shoot a flitable and measure the surface pressure at the well. This valve is closed right now, so you have to open the valve before you can shoot the flitable. These are the power probes connected to the panel to measure the power and the amps during pumping. And this is the horseshoe load cell that we have the rod strings stacked off on the well, and we've created a 3-inch gap to be able to place the horseshoe load cell between the polish rod clamp and the carry bar, and then we'll remove this suitcase, and the entire rod string weight will be resting on the load cell, and we weigh it just like you weigh yourself on a bathroom scale. Now this is the wireless equipment, and this is called the base station, and we have a power probe attached to the panel, and you can either attach it with cables with a harness, and it's portable, or you can install a permanently fixed power connector, and then you can attach the radio, and while you're pumping, you can have line of sight to your base station that would be probably inside your vehicle or on the back of your tailgate. And here's the software showing that we're acquiring dynamometer data at the same time we're shooting a flitable. And we also can measure the tubing pressure. So there's a lot of information we can measure at the same time with the wireless system. And it's a little bit faster to use the wireless system because the tool has buttons on it to turn it on and off. You don't have to walk back and forth to the software to hook it up to the well. So it's just a little bit faster to use to acquire data. Now these are the gas guns, and there's different types of gas guns. And a long time ago, the gas guns that we used black powder. And so you would walk up to a well and you'd attach a gun to the casing of the well. And when you would fire a shot, you really would fire a 10-gauge shotgun shell off into the closed casing annulus of the well. And as long as there wasn't any oxygen present, it'd be safe to do that. And a few times, there was casing leaks where the air could leak into the casing, and the casing blew up in one well up in Canada. So people in the 1980s started outlawing the black powder guns. So this gun is called the compact gas gun. It has a volume here that we charge to a pressure greater than well pressure. If you raise this lever here, it cocks it. You pull that ring, it releases a valve and fires it. It's got a microphone in here that measures the change in pressure. Now, when you shoot a flitable, the change in pressure is the echoes from the shot being fired from any change in the wellbore diameter, like a collar or a tubing anchor or perforation or liquid level can all make echoes. And so when you shoot this pressure into the well, you push on the gas at the surface, and the pressure from the gun travels down the well and echoes off back to the microphone. That creates an acoustic trace. Now these two gas guns, this is wired and this is a wireless gas gun. And the advantage this gun has is when you push the fire shot button on your laptop or push a button on the keypad here, the gun will fire automatically. And so the computer control the gas gun. And the other advantage it has, the microphones are the same in these two guns. They're very sensitive at pressures less than 1,500 pounds of pressure. But the other advantage is that you can take this volume chamber off and put a much bigger volume chamber on the gun, which means you put more pressure and gas into the gun to fire the shot. And that makes bigger echoes, and you can see deeper into low pressure or noisy wells. Now these three gas guns here, this is for wells that have pressures up to 15,000 PSI. And these two gas guns this is wired and wireless, and they can go on wells up to 5,000 PSI to shoot a flitable. But basically they're all the same. They all have a method to open a valve quickly. They all have a method to measure the pressure at the surface, and they all have microphones in the gas gun to record, to produce a signal from the pressure at the surface of the well and the echoes, the change in pressures at the surface of the well. And that's basically what creates an acoustic trace. Now here we have a video, a little animation that shows the gas gun attached to the casing, and we're going to charge the gas gun. This is the cylinder CO2. Charge the gas gun to a pressure greater than well pressure. We open that valve. We send a signal to the solenoid that quickly opens the valve in the gun and sends that pressure wave down the well. The pressure wave travels through the gas column at the speed of sound. The acoustic velocity is the speed of sound, and every change in cross-section like a collar rips off a little piece of that pressure wave and sends it back to the surface and recorded as an echo at the surface. So we can see every little collar, usually close to the liquid level, down close to the liquid level, and it's traveling and it hits the liquid level, the pressure wave, and it echoes back to the surface. And when it gets back to the surface, we will have recorded the shot going off and the echo from the liquid level, which is round trip time. And then we can use the round trip time divided by 2, because it goes down and back, times the acoustic velocity to get the distance to the liquid level. And also we have this pressure gauge here that's recording the pressure, measuring pressure at the surface. And then we measure pressure over a period of time, maybe just 2 minutes or maybe longer. And since this valve on the other side is closed, then the gas that's being flows by the pump makes this pressure at the surface of the well go up. And we read the pressure, and the change in pressure versus time represents the gas flow rate in the casing. And it also represents the bubbles that bubble through the liquid above the pump. And then we use that pressure buildup to calculate the weight of the fluid above the pump, so we can calculate the pump intake pressure and the producing mile pressure. So that's a short, 2 to 3 minute test. Doesn't take very long to do a test like this. And you always take 2 shots in the well to make sure that they repeat. And the software typically, by default, counts the collars. The collar echoes determine the number of joints to liquid. And that's typically how we, by default, determine distance to liquid level. Now here is Jim McCoy, or Rusty. This is Rusty. He builds some of the equipment at Echometer. He's going out to the well, and he's going to remove the bull plug from the well. And this is the casing valve. We're going to attach the gun. He's going to check for any damage or debris in the valve. And the valve is closed, and he's going to come back and bring his remote fire gas gun. He's going to attach the gas gun to the well and make 4.5 complete turns to make a safe connection. And he will check the pressure on this gun, on this well, before he attaches the gun, and make sure that the well pressure doesn't exceed the working pressure, 1500 psi of the gun. And then he'll be able to, when he charges the gun, fire a shot. Now this is a wired system, so he's attaching a pressure transducer. The wireless gas gun has a pressure internal to the gas gun. He's attaching the microphone cable right there. He's already attached the solenoid cable. Now he's attaching a cable to the pressure transducer, and we call that a pressure transducer solenoid cable, or a Y cable. Now he goes back to the laptop at the back of his truck, and he attaches a microphone cable to the wired well analyzer, and then he also attaches the cable for the pressure transducer to the well analyzer. Turns the well analyzer on, starts the software, and then he would load the software to. This is a TWM software, and here he's going to go and perform a 0 on the equipment. And so that's the steps to fire a shot. And we're checking the equipment, make sure we're communicating. This shows the battery voltage, and as long as the battery voltage is above 10 volts, then we can acquire data with the gas gun and the well analyzer. Now this is the new TAM software, and we push the take to shot button, and there's our shot being fired, and here's the collar echoes coming back. And this is in seconds, we're taking the 1,000 data points per second from the microphone. We're looking for a big kick. There's a big kick right there, and that's likely the liquid level. And liquid level is about 9.5 seconds from the surface, 9.521 seconds. And we're measuring the pressure. And so we're measuring the pressure at the well, and the software automatically determine the number of feet above the liquid level. And if there's gas pressure building up, then it will adjust this height of the gassy fluid column to be adjusted based on gas bubbles flowing through the liquid. And here we use, this is a wireless gas gun that we used. And it shows that we have good communication and the battery is fully charged inside the gas gun. So this is just an example of acquiring a fluidable shot on a well. Now, when you fire a fluidable shot on a well, you're really not done. The important part is to make sure you install the gun and acquire good data, make sure the well is stabilized. But once you get the data, then you need to think about, where is the liquid level? Is the liquid level above the pump? Well, it should be. Well, if it's a well with a pump, what if it's not a well with a pump? Well, if it's a gas well and the casing valve is closed, liquid level is probably going to be down at the end of the tubing, and the liquid and gas are going to be flowing up the tubing. What is the percentage of the liquid in the annulus above the pump? What that means is, if gas is flowing through the liquid above the pump, then those bubbles of gas make the liquid lighter. And so we measure the pressure buildup and we calculate with the correlation that Echometer developed back in 1986, a long time ago, based on a field measured data. We developed this correlation, and we use that correlation to calculate how much gas is present and how much the liquid in the casing above the pump weighs, and then we can use that to calculate the casing pressure, since we measure the pressure at the surface and we know the weight of the gas based on the acoustic velocity. Now, if the pressure builds up, that means that gas is flowing up the casing. And so if pressure is not building up when we shoot the fluid level, that means there's no gas building up the casing. If there's no gas building up in the casing fluid shot, that should mean that the pump ought to be full of liquid because there's no free gas. And if the pressure is building up, then we calculate based on the area of the casing ID minus the tubing ID and the distance to the liquid level, we calculate the gas flow rate. And it's a reasonably accurate gas flow rate from the well. Is a well efficiently being produced? That means, is the bottom hole pressure measured, calculated, while the well is producing, low compared to the static pressure? How low? Well, it needs to be about 10% of the static. And Vogel would say that that would produce, you'll be producing 97% of the liquid, maximum liquid production rate. Now, when the casing pressure is high, that casing pressure adds to the weight of the liquid, and that makes more pressure on the formation, and that restricts the inflow from the formation in the wellbore, and that can cause you to not have a high production rate. Or liquid can also cause a restriction to inflow. If the liquid level is high, or if the casing pressure is high, either one or both can cause you to have a high producing well pressure and not be efficiently producing the well. And then based on the producing well pressure and the current liquid production rate and the reservoir pressure, then we calculate the maximum production rate from the well. If you could draw the bottom hole pressure to pump intake pressure to 0, well, you probably can't get that low, but it gives you an idea how much fluid you should be able to get out of your well. Now, this is a report out of the TAM software after you shot a fluid level. And this is the answers to the questions like, here's the distance of the liquid, and here's the effect of the gas, the feet of fluid above the pump. This is your maximum production rate from the well. The potential, a little bit more. So we're producing pretty high, because look, the fluid level is darn close to the pump. So this shows a little picture with the fluid level down close to the pump. You can, there's a tubing anchor echo, and there's liquid level echo. You can see the percent of liquid, 75% liquid above the pump intake. You can see how fast gas is flowing up the casing. Not very much gas, 3.6 MCF, only 4 MCF of gas. That's not much, but that makes the liquid here 25% gas and 75% liquid. So it has a big impact on the weight of the liquid column. And these are shown in meters. You can put meters or feet, whichever unit you want. And then here's the pump intake pressure, the reservoir pressure from producing well pressure, reservoir pressure, and the pressure at the gas liquid interface right there. And then the casing pressure building up, so we got gas flowing at a certain rate. And we calculate, based on the acoustic velocity, the the gas gravity. So right down there is a gas gravity used from using the tubing anchor. So you can see the tubing anchor echo, and we use that to determine distance to liquid. So that's another method to determine distance, not just counting collars. You can see the collars very clearly here. Those little lines there are collar echoes, but you can also see a tubing anchor, and that's very close to liquid level. So if you can see something close to liquid level and you know the depth of it, then you can use the distance from here to that anchor to determine the distance from here to the liquid level. Now this just shows pressure versus depth, and what we're trying to show is that here is the pressure versus depth in the tubing, and that's the pressure at the top of the pump called the pump discharge pressure. And then the pump discharge pressure, this is the pump intake pressure, and we said so the pump is able to take the pressure at the pump, and that pressure at the pump is what we drew the well down with. So we drew the pump's able to draw the well down this much, and this amount of drawdown is what's causing the well fluids to flow into the well. And so here's our drawdown from here to here, and this is our liquid column here above the pump, and here is our high fluid level. This is probably water below the pump and oil above, and then there's our fluid level. It's pretty high, and there's our surface casing pressure. And so this is the pressure in the annulus of the well versus depth, and the well's about 5,000, probably 200 feet deep. And then this is the pressure inside the tubing, and so here's the pump intake pressure, and the pump raises the pressure at the bottom of the tubing to discharge pressure due to some method. This is probably a rod pump well, probably just compression. And then the compressed fluids flow from the pump discharge all the way to the surface to this tubing pressure, which is probably 80, 90 PSI, not very much. Now, we also talked about the device that you can weigh yourself with, but we're going to weigh the rod string. It's called a dynamometer. And then we use the load we weigh, the weight of the rods at the surface along with the pump load. We use that load at the surface that we measure along with the position of the polish rod. Or the position of the polish rod we determine from an accelerometer. Now, an accelerometer is what you have in your vehicle or your cell phone, and it measures the change in velocity. So we measure the change in velocity with the accelerometer, and that gives us a position versus the time of the stroke. And the load versus time, we plot the load versus position. We call it a dynamometer card. So we can determine based on the surface dynamometer card and what's down at the pump, is the pump full or is it partly full? If it's partly full and it's not full of high pressure gas, we say, well, the well's pumped off. And you need to slow the well down. It's pumping too fast. We can use the pump card, the height of the pump card. We'll talk about that more. Determine the pump intake pressure. And then we calculate automatically how much liquid's in the pump. We adjust it for slippage. We adjust it for free gas in the pump. And we can calculate an adjusted pump displacement and tell you how many barrels of liquid should reach your tank based on your dynamometer and out collection data at the well. Since we're measuring acceleration, we can determine the pumping speed. We can see whether the valve that's on the upstroke, called the traveling valve, is leaking and the suck rod pump down at the bottom of the tubing, or is the valve at the bottom of the tubing, called the standing valve, that's supposed to hold the liquid in the tubing on the downstroke, is it leaking? We can see that based on the shape of what we call the pump card. We see the maximum load on the rods, the minimum load at the surface on the rods, and we see if the rod string's overloaded and is there a chance for the rods to have a short life. We look at the load of the polish rod and the versus position and the load at the pump versus the position of the pump. And the area, the plot, is the horsepower. So we can see if the loss in horsepower from the polish rod to the pump. We can see if the gearbox is overloaded, and we can calculate where we should move the weights on the crank so that the gearbox won't be overloaded and have a reduced life or be damaged. We calculate the inches of movement from the current position to a balanced condition. And then if we have gas in the pump, we can see that our downhole gas separator is not effective. So there's a lot of this is from the data you collect at the well. There's a lot of things you can understand about your well just by taking a simple measurement at the surface. So here's these different dynamometer devices. So this is the clamp-on device for the wired system called the polished rod transducer. This is a wireless one. And again, notice it's got buttons. You walk over to the well and you put it on the polished rod and you just push the button to turn it on and start acquiring data. This is we call the 50K load cell. And this one is a 30K load cell. We have both wireless and wired 30K and 50K load cells. So the 30K load cells, the throat here is 1.5 inches, and it'll go around 1.5 inch polish rod. And so to put this on the well, you have to put a suitcase on the well and rest the entire rod string weight stacked off and not damage your packing. And then make a gap that's more than 3 inches to put this in there, and then you release this load back onto the load cell. Well, that's kind of a hassle. So the other way you can do this is you can put a washer on the bottom and a spool around the polish rod right there, and a washer on the top below the polish rod clamp. And the spool is 5 inches tall, and this load cell right here is 4.9 inches tall. You can just walk up and place it right there, quick and easy. And then there's a little spacer plate you slip in between the load cell and jack after you pumped it up with this hydraulic pump. You make a 1/4 inch gap there, and you can stack it off very quick and very safe. So the advantage of the load cells is they're very accurate and they actually weigh the rod string. The advantage of these devices are they're quick and easy, and people tend to like to use these a lot because they're so fast. The other option you have is you have a pump off control system, or you have permanently installed, we call these donut load cells, or pump off controller load cells already installed in your well. Then you can send us a cable and we'll fix your cable to hook into an accelerometer or the wired polished rod transducer. And you can use your load cell for load and our accelerometer from the polished rod transducer or the special accelerometer here to get the position of the polish rod. So this is kind of an interesting picture, because what we're trying to show here is that this figure here we call the surface dynamometer card, and it is measured with some type of load cell attached to the rod string, the polished rod transducer horseshoe load cell. And so this is inches of stroke along this way. And so here's our upstroke right here. And then here's our downstroke. Okay, and this is our peak load, our minimum load that's acting on the rod string. And back in the 1960s, a guy that's a physicist derived a thing called the wave equation, a mathematical model. And what he provided was a mathematical technique that a computer would have to solve and run that calculates how these loads and position velocities move through the rod string like a wave from the surface, from that point down to the end of the rod string right above the pump. And so this figure right here represents the load that the pump, this trailing valve applies to the rod string. And so when you look at this, you see some interesting things. You see that well, first of all, what is this? Here we pick up the fluid load. From B to C, we're carrying, what happens right there is the standing valve opens. So the standing valve ball pops off the C at that point, because now the pressure inside the pump chamber has dropped below the pressure on outside of the standing valve. And so at that point right there, the full tubing pressure from the surface all the way down to the pump is being applied to this trailing valve. And the well might be helping a little bit. So the difference in pressure from above minus the pressure from the well is the differential pressure acting across the pump. And it's fairly constant because that line's fairly flat. And so the plunger is moving up from here to here, and well fluids are entering the pump chamber through the intake valve. And then right here at the top of the stroke, both balls go on the seat and we compress the fluid. And right there at the point D, what happens? Well, this trailing valve pops open and there's no load. See, This is no load, zero load. Well, not quite, about zero load. As the plunger moves on the downstroke from this point to that point, displacing fluid into the tubing on the downstroke. And that's what this pump card represents. So when Sam Gibbs back in 1960s derived the wave equation, we were able to then start using computers. Well, the computers weren't very good back then. Big mainframes, and eventually we got the portable computers, and we could take this software out to a well and see what was happening at the bottom of a well with this pump card. Now I want to just show a couple more things here. If I were to weigh this well with a load cell and weigh it right there at the top of the stroke, it's 14,820 pounds. And the rod string and fluid weighs 10,400 pounds. And if I were to subtract that, it would be 4,400 pounds. Well, the load right there, minus weight rods and fluid, doesn't equal 6,280 pounds. So that sometimes that doesn't make sense. Well, what happens here is the rod string's moving, and so there's acceleration forces. And so when the acceleration forces are there, like this is a minimum load due to acceleration. You have to use a wave equation to process this data to come up with what's really happening at the bottom of the rod string. All right, now this is a well where we've acquired data, and this is the data at the surface. This is a surface dynamometer card. And then down here at the pump is the calculated pump card. And so when you acquire data with an Echometer system with a new version of software, it shows you after a couple of strokes what's happening at the surface and what's happening downhole. And it shows where the valves open and close. And this well has two things going on with it. The pump is full, and so this is a full card. There's no gas in the pump. The pump intake pressure is low because this loads up here at the maximum load line, and it's showing that the tubing is unanchored. And so this line right here is where that line right there in red called unanchored tubing is the line that this should follow if there's no slippage. Well, since there's slippage, what's that mean? That means on the upstroke, when this troweling valve is carrying the load, liquid is slipping either through the ball and seat area or between the plunger and the barrel, and the plunger moves without picking up any fluid load. And so it leans over even more. So this is an example of a well that has a full pump, low pump intake pressure, but the pump's warm, and the tubing is unanchored, and unanchored tubing will cause a hole, rod on tubing wear, and a failure. And so this picture here is what's happening down at the bottom. And this picture here is what we measure at the surface. And here's all these parameters along the side that are calculated that you can use to answer those questions we talked about a minute ago. So here we have the rod stress. This is called a modified Goodman allowable, and it says if you're outside this range, like right here, then you exceed the allowable and your rods are overloaded. If you're inside this gray area, you're not overloaded. And so we take these peak and minimum loads and we calculate the stress range and see if we're 77% loaded, so that we're okay. Now this is called a permissible load diagram. That's for torquing the gearbox. And if this load right here goes above that dashed red line, it means that we're overloaded and we're damaging our gearbox. And so we calculate that this pumping unit is overloaded by 8%, and based on information from Lufkin, Cecil Hunt, the chief engineer, sent this to us, and it says that at 8% overload, 8.8% is going to reduce the life from 25 years down to 12 years. So just a little bit of overload in the gearbox can cause a shorter life. And you know, if you overload at 25%, your gearbox will fail in 3 years. Motor power. Motor power is measured usually, it doesn't have to always be, but usually is the same time you're using a rod pump well. We can use it to determine the efficiency of the pumping system. Normally, the surface efficiency from the panel to the polish rod is about 80%. If it's much less than 80%, then there's some kind of bearing at the surface that's probably defective, or it's way out of balance, or the motor's damaged. The overall efficiency from the panel all the way down to the pump is normally 50% if the pump's full of liquid, and the unit's in good operating condition, and there's no mechanical rod-on tubing wear. And so 50% is a normal efficiency. Usually use about half the power to produce the fluid to the surface. We can calculate the dollars per month per barrel, the power demand, and we calculate the kW use. We can see how much current's going through the motor, and if the motor is thermally loaded, the thermal rating of the motor will be exceeded, and you'll be having motors that burn up, and you can see that by measuring the current. The motor, when it goes through the cyclic loading, depending on the type of pump unit that you have, it's going to have the weights falling and push the motor faster than 1200 RPM, and it'll generate power. In some cases, you get credit for the power. In some contracts, you don't with the power company. We can see if just based on the kW, is the gearbox overloaded. You can see where to put the weights. You don't have to have the geometry of the pump unit to do this, just a motor kW versus time. How far to move the weights. And then we also now, with the wireless equipment, we can calculate if the wire coming to the pumping unit is too small from the transformer, are we heating the wire up like a toaster and losing power? This is the power probe harness, these wires, for the wireless system inside the panel. And there's a radio antenna, and we need to have direct line of sight and not a person between here, because a person even will block the signal a little bit. And so we can receive the signal from the panel. The limit right now, I think the distance is up to 400 feet. This is the information that we acquire with the wired and wireless power probes. We have the cost per barrel per month. We have the motor that we have on the well and what motor we could use, which is, we couldn't use a 20 horsepower, but we could maybe use a 25 horsepower on this well. Because the efficiency is not very high. It's 33%, which means that there's an issue with this well that is causing the producing efficiency to be too low, lower than 50%. And we can probably find some problem on the well and repair that, fix that problem, and make the efficiency higher. Now this is, the black line is the power net torque, and the red line is the torque from the motor power, and you can see that they both show the same thing. This peak torque this is the downstroke, this is the upstroke. The downstroke power or peak torque is too high, net gearbox torque. And so we need to move the weights in a little bit, and it says how much to move the weights in, the software does, to balance the pump unit. So it's another thing it tells you based on mechanical or motor power. It's where the weight should be to reduce damage and be more efficient. Now these are the reports. This is the little report here we've already kind of talked about a little bit. And this is a Dynamometer report that shows the answer to those questions. I don't have them highlighted in red, but the report's a PDF report that you can email to someone. You can print it out. You can save it, store it on a server somewhere. So someone that's not familiar with the software can just open up the report and see what you may have recommended here, be recommendations about as well. Now, you can use the equipment on other lift types, and this is a hydraulic pumping well. It's a long stroke, and so as long as we have access to the polish rod, then we can measure the diameter changes of polish rod. And this is a Dyna pump, and these are other hydraulic pumps. And this is pumping fairly slow. So if you look at this, you can see the load's fairly constant, even at the surface. And this is the load on the downstroke. And so this is a long stroke hydraulic pumping unit, and they're typically not as efficient unless they're counterbalanced. So this system has a lot of energy lifting the rods, and the rods just fall on the downstroke. This system has a nitrogen cylinder here, where the nitrogen cylinder is compressed, and then on the downstroke, the nitrogen cylinder resists the fall of this piston here, and it's more efficient. So counterbalancing makes rod pumping the very efficient lift system. We also have different types of tests we can do. We can do multi-shot testing, which is called pressure transient, and that's the test that you would do when you shut a well in, and when it's pumping steady state, and you would measure the change in the pressure versus time, and that tells you if the change in pressure is what? If the change in pressure is changing correctly. It's kind of a weird way to say it, but if the well's not damaged, then the pressure is going to build a certain way. And if the well is stimulated, then the pressure is going to increase quickly. If the well is damaged, then it's like a dam of damaged material around the wellbore that's going to prevent the pressure increase. And so you can identify a well that's damaged with a pressure transient test, and then you can stimulate it, and it's like getting a brand new well, because now you've removed the damage with your stimulation. We can track plungers and see how fast plungers fall if they get stuck. We can shoot down gas lift wells and find leaky checks, holes in tubing, and what valve you've lifted down to in the past. And we can look for liquid loading and flowing gas wells. So we do all kinds of tests, and we're talking about these tests. So on a gas well, you can see again if gas is flowing, what rate. You can see the depth to the top of liquid. You say if the liquid above the pump, where is it in the tubing? You can determine the percentage of liquid based on the gas flow rate. You can see about restriction of flow based on the pressures. You can determine the amount of back pressure acting on the formation by liquid accumulated in the tubing. Or we can determine the producing of static bottom pressure. We can determine if the pressure buildup pushes liquid out of the tubing. Again, we can determine what the maximum flow rate is. So here's a gas. These are gas wells right here in the pictures. And these are wells that we've shot down the tubing. This is a well in Holland with a remote fire gas gun with a large volume chamber. This is the compact gas gun attached to a plunger lift well. This is a 5,000-pound gas gun attached to a well flowing above critical rate. And here's the gas gun shot down the tubing. Here's our fluid level in the tubing, fairly high fluid level. And we've calculated the liquid in the tubing and say this is how much condensate we have, and this is how much water, based on the ratio of the oil and water. And these are not quite one, and there's a little more condensate than water being produced in this well. We also can plot the pressure versus depth. So here's the pressure versus depth in this well if the tubing is full of gas and it's flowing. And here's the pressure versus depth when the liquid level is right there in the tubing. And so this represents the back pressure acting on the formation that's restricting inflow, and the back pressure is 630 psi. And we figured that out just from the fluid level shot. And it says if you had a much smaller size tubing, a capillary string, or probably drop some soap sticks, doesn't say that, but you could increase the production rate of the well by almost 100 MCF per day. And it calculates this based on something we call a nodal analysis, but it's a nodal analysis for flowing liquid loaded gas wells. And we're saying we can take the back pressure away. There's the extra pressure to the liquid. And if we remove the back pressure, this is a drawdown, the additional drawdown we'll get. That would result in 100 more MCF per day if we could get this liquid out of the well. That's called a liquid loaded well. This liquid is pushing on the formation, restricting inflow. Now here's a well we shot a fluid level on. It's a gas lift well. And we can turn on a filter called low pass filter in the software. And now we can see the kicks from each of the gas lift valves. And if you shot down the back side, that casing side, you'd see down kick. And if you shoot down the tubing and have mandrels, you'll see up kicks. So it depends on the kind of gas lift well you have. And here I've overlaid the wellbore to show that you can use these markers, these gas lift valves. And here's a gas lift valve right there. And there's gas lift valve that depth, and we can identify the gas lift valves. And the direction kick sometimes can be used to tell us we've got a hole or a kick that doesn't belong there. And then we use the deepest gas lift valve to determine distance of liquid. And that's the downhole marker method. Now here's a fluid level shot, and we shot down the tubing. And when we come to the mandrel in this well, these are probably more mandrels offshore. Most onshore gas lift wells have the conventional, where the gas lift valves just attached to the outside of the tubing. But here, if we shoot, you can see there's a big increase of the mandrel, and you can see the upkicks right there. And if we shoot down the casing, here's a casing shot, and those kicks are down. And so the direction of kick depends on whether there's an increase or decrease in the cross-sectional area of the wellbore. All right, here's plunger lift. And we got a gas gun on the tubing, listen to plunger, and here's a pressure sensor on the casing. And we can again answer these questions. There's just questions we can see, like how fast the plunger falls, where the plunger is, does it get stuck, things like that. We can answer these kind of questions. And here's the data we collect. Here's the pressure in the casing versus a cycle. Here's the pressure in the tube versus a cycle. And here's shut in from this point to that point. Here's unloading. Here's the acoustic signal, and there the plunger's falling. You can see the plunger falling. You can see the plunger at liquid. And then it's on bottom about right there. And we have, after we process the data, we can animate the plunger and see and stop this any point in time. We can see the plunger falling down the well. We can see the plunger fall velocity. Here is the plots versus time. These are called analysis plots. And we got a plunger depth in green and velocity in red, and a casing pressure and tubing pressure. And there's many different types of plots we can make. And so I think we're kind of running out of time. And so this last part, I'm just going to show a couple of slides. This is a new device this is a normal way we use the wireless equipment. You're at the well with a laptop, the base station, wireless communication, the sensors attached to the well. One of the things that we're developing now is something we call a remote asset monitor. And we replace the person at the well, not really at the well, he's back at the office. And then we leave a device called a RAM out at the well, hooked to the base station. And this device can access the internet through a cellular modem or internet access. And then you can do the same thing from your office that you can do at the well. But here you can schedule tests and collect data over a period of time. So I think I've kind of reached the end of my time, and I'll stop for questions. Anybody have any questions, Tawny?
I will. So far, I only have one question that I saw in the chat, and it was, do you have a class for plunger lift tracking?
It's pretty short, but we have a 5-day class that we teach. Yes, we have a class that we teach, and I would have already taught 2 classes this year, but we've canceled those classes. So the class that we have right now is fairly short. It's only a half a day, and we have one 2-hour presentation on Ask Echometer. So that's the current online resources. And we could, if you have a question, you should just, if you have data, you can surely email us data, and we'd be glad to answer your questions. And if enough people wanted to, we'd probably set up a class online and do a Zoom class, but probably wouldn't do a full day class because it gets kind of boring to listen to someone talk on the computer for a full day. So we probably only do half-day classes is what we probably would do. But we have all that material. I've been teaching classes on plunger lift with Jim Lee. He wrote the book on deliquefying gas wells. We've been teaching that class since 2005. So yeah, we published a new book. Jim Lee and I published a new book about a year or 2 ago. But anyway, yeah, we do teach classes, and we're very interested in doing that. And again, I put my contact information at the front, and there's also Kylie's contact information. If you're interested, contact her, and we can probably set something up.
Awesome. Okay, so now we have a few questions. What's the best pump to run with wells still making sand?
Well, subcrop pumps really don't like sand, and so the pump either can be, there's a pump called a Muth pump that has a very tight clearance. Or you can put a very open pump clearance because the sand grains will fall through. But if the sand gets between the plunger and the barrel during pumping, that scores the barrel and reduces the life. So Weatherford and another company come out with a thing called a sand shield. It's kind of like a plunger at the top of your trailing valve plunger that contacts the tubing and keeps the sand from falling between the plunger and the barrel. So I don't really, if you have a lot of sand, sometimes that limits your ability to use the suck rod pump. And another thing that limits the suck rod pump use is wellbore deviation and lots of gas. So when you have a really tough problem like that, you may, this sounds terrible, but you may want to consider using gas lift. But you've got three choices in my view. Four. You try to clean the well out so you don't have a sand problem as much as you can. So anytime you have a failure with sand, you clean the well out. And that's really important on vertical wells. It's tougher to clean the sand out on horizontal wells. So try to clean the well out. Then you have either have really tight clearances like a Muth pump, or you have open clearances and you need to be concerned about slippage. And the slippage calculator we have in our QWOD program will let you calculate the barrels per day slippage, so you can design your pump to pump both the slippage and your desired pump rate. And as long as you make the clearances open enough, the sand hopefully will fall through. But then, if that's not going to work, you can put a thing called a sand shield that has been proven to keep the sand from falling between the plunger barrel and the tubing, barrel and the plunger. Dang it! Keep the sand from falling between the plunger and the barrel. And that's just like a brush that runs above the plunger that seals off this gap between the plunger and the barrel. Okay, that's kind of a long answer. But anyway, that's what I recommend.
Okay, so this says, Lynn, I have a Model D that I used up till a few years ago. Can a person still get paper and a new battery?
Yes, you can get a battery and you can get paper. And but the Model D is the last one we built and sold was like 1994.
Wow.
So it's probably, if you break a wire in it, or if you have a part that goes bad, then we can't repair it because we don't have any more parts. But we do have paper for it, and we do have batteries. So there's a lot of old time electronic components that are not anywhere made anymore in the whole world. So if you want to replace that, we have a device called a Model M, and it can be purchased, and you can still use your gas gun. But my preference, this is like an advertisement. My preference is to use a computerized well analyzer because you get a lot more information, and you're better at analyzing your well with a computerized system because it shows you distance of liquid. And I don't know, I've always just used computers all my life, so I really like the computerized system, and you can still use your gas gun even with the computerized system. So that was kind of a commercial, sorry.
That's okay. Okay, we have two more. Is there any minimum depths or pressures that you could not work with? For instance, with very shallow producing wells, less than 1,000?
Yeah, well, so that's a good question, because the answer is no. But the answer is, okay, if you have a shallow well and you shoot it, and our fluid level that's, let's say, 15 feet from the surface. So when you shoot it, then if you put too much pressure in your gas gun, you just want to use a little bit of pressure in your gas gun over the well pressure, so you don't put a bunch of energy in the well when it have a really high fluid level. And then when you shoot it, if you have, let's say, 100 pounds of pressure, that echo just bounces back and forth really, really fast, and it gradually dies out. And if you can imagine this, it looks really big at the beginning of the shot, and it just kind of looks like a funnel. Or a tornado, it just goes from big to small as it goes, and time goes by. So when you look at that, you say, "Oh, I got a fluid level that looks like a tornado or whatever, funnel." And then you have to use the software to go look near the surface of the beginning of the shot, identify the kick, and you can determine the thousandths of a second to liquid level. and every 1,000th of a second is like 6 inches. And so, yes, you just have to work a little bit harder at it because you have to put not too much pressure. And then you have to identify the kick. And and now, then on the wells that are less, a second of data is about 600 to 700 feet. And so if the well has a fluid level deeper than 700 feet, then the computer will probably pick the right liquid level, or it might pick the second liquid level echo. It's another 700 feet down, and you still have to go look at it and move the indicator for liquid level to the first echo. So the high fluid levels are harder because the software normally can't automatically pick it, and so you have to. It's not a problem. Once you learn how to do it, it's no big deal. But at first it's confusing, and then you just email us your data, and we'll help you, and you'll understand how it works. So yes, it'll work shallow wells, and it works really deep wells. You just have to have more pressure when you shoot really deep wells.
Okay. Very last question that we'll take for today is, can you use this study for horizontal well?
Oh yeah, most of our equipment right now is being used on horizontal wells because those are the new wells that are being drilled. And I don't think hardly anyone's drilling a vertical well anymore. So let me just kind of give you some unique examples. Normally, when you have a rod pump well, the fluid level is at the end of the tubing. Even in a horizontal well, the pump won't pump unless you have fluid near the pump. And sometimes the fluid level could be above the pump. But in gas wells and plunger lift wells, the gas flows up to the tubing to the plunger, and often in a horizontal well, the gas is on the top and the liquid's on the bottom of the horizontal. And so sometimes you shoot a fluid well, you can see out into the horizontal and see perforation upkicks. So the wells are, and a deviation survey is important if you're trying to calculate pressure. So if you have a horizontal well, then you need to not be surprised that you can shoot past the end of the tubing if it's a gas well or a well that would be flowing, because the liquid will segregate. And you need to have better information about the well, the deviation survey, because we want to adjust the pressure for vertical depth, not measured depth. The fluid level is measured depth. And we want to adjust the rod string weight for the vertical weight, not the weight of the whole rod string, because some of the weight of the rods are laying on the side of the tubing. So that's the answer. Yes, there's no problem at all. We do it all the time. You need to understand that you might see some things different than a vertical well, because in fact, I've seen flow shots on plunger wells where they shot down the tubing and the well made maybe 1 or 2 barrels a day of liquid, and the horizontal well slightly tilted up toward the end of the horizontal of the toe, and the guy, when he shot all the way out to the end of the well, because the liquid's on the bottom, the gas is on top. So that's a little bit different than a vertical well, but yeah, you can absolutely use our equipment on horizontal wells without any trouble.
Awesome. Okay, so I lied. We have one more question. Is the Model H able to determine high fluid levels with self-computing?
I'm not familiar with the Model H. Carrie Ann Taylor is the engineer at Echometer that uses Model H and does training on it. And it has a really good downhole marker method in the Model H to determine distance to liquid. And you can move the liquid levels, and it has the same acoustic trace. So you probably, if you shoot a high fluid level, you've got to use a manual method to select liquid level, and you may only be able to type in acoustic velocity. But anyway, so the Model H is designed for environments where there might be an explosive gas. And so if you go into an environment where there's hydrocarbon gas that could explode, you want the device to be certified to not create an explosion. And that's called intrinsically safe. And so a lot of the Model H's are used offshore. They're used inside buildings up in Alaska, where the building's a confined space and explosive gas could collect in that in space. Currently, the Model H's are sold out, and we probably have at least 6 months before we have some more Model H's. But yeah, we'll have certified wireless gas guns and the Model H here fairly soon. That'll be available that you can purchase if you want. So the answer is yes. You can find a high fluid level with the Model H. It may take more work, just like a regular the regular acoustic instruments, because the software has a hard time picking the liquid level. All right.
All right. Well, thank you guys so much for all attending. I want to thank Lynn with Echometer for putting on this great webinar. If you guys have any questions, please feel free to shoot me an email. I put my email down in the chat, but if you didn't get it, it's tklaus@soarok.com. Thank you guys.
Connie, did you send a link to the
Thank you, everyone.
online the recording of these seminars? Where's that going to be at?
Yes, so I will have that on YouTube, and usually people will say, hey, can you send me that? And I will definitely send that out to anyone.
Okay.
All right, thank you guys very much.
Thank you.